We need to build physical models of what I call structural memory. Design in nature uses this memory to build the most structural integrity with the least investment in material, space, or effort. Natural design remembers what worked in the past. Synergy is the behavior of whole systems unpredicted by the behavior of the essential parts. There are communication networks that link these parts into an integrated whole, synergy. That is what a structural memory is, the communication among the essential parts of a fundamental structure. Let's explore these ideas in the context of the synergy between the two fundamental job description families, the sphere and bubble families. Spheres, circles, and triangles are embedded with this synergetic memory. The 12 spheres that construct the first closest packed layer around our blue U-Me ball are an effective physical model of these memories. These spheres construct a 2BB edged vector equilibrium, VE. The spheres are placed on the three beginning landmarks, the equator, axis of spin, and the relative size field, which orients them into our standard position. You can see the 50 directions lines of communication of the sphere family grew out of this arrangement of spheres. The center is connected to the three outside limit locations in common. The 12 white directions pass through the center of the spheres and define the outside corner locations. The 24 yellow directions pass through the tangent or kissing point between the spheres and define the midpoints of the outside edge. The 8 blue directions pass through the 3-ball gap to define the center of the triangular faces of the VE. The 6 green directions pass through the 4-ball gap to define the center of the square faces of the VE. There are 14 directions in common between these two families. Where do they come from? We will construct a cubic containment field around our 6BB VE. To find any synergy around structures, use a 3-step process. Measure relative to your scale number and location, map the interconnectedness from the center out, and contain this order with an outside containment field, its maximum limit. In a cube, the white directions now define the midpoints of the edge of the cube. The 8 blue directions define the outside corners, and the 6 green directions remain at the center of the squares. We will leave out the 24 yellow directions for this exploration. The 14 directions in common are the 8 blue directions and 6 green directions. Because we oriented our structure with the 3 standard landmarks, they will always align from the center out. The sphere family has 12 white directions that define the outside corners of the VE. The bubble family has 12 red directions that define the outside corners of the icosahedron. Anytime you want to fit an icosa inside a cube, multiply the edge by GR, the golden ratio. The long axis of the square face of the VE is the same length as the edge of the cube. Multiply the long axis of the squares of the VE, and you will have the size of the icosa that fits exactly inside. There are 60 directions in the bubble family that are organized with the same 12 spheres as the sphere family, but with the central U-Me ball taken out. This rearrangement defines the communication network of the 20-sided icosahedron. This family uses the same pattern of organization with slight variations. The sphere family had 12 white directions that pass through the centers of the spheres. The bubble family has 12 red directions that pass through the centers that define the outside corners of the icosa. It is now easy to differentiate which lines of communication are in which family. There are 20 blue directions passing through the 3-ball gap that define the centers of the triangles. There are 30 green directions that pass through the kissing points between the spheres that define the midpoints of the outside edges of the icosa. The other 3 systems of this layered family connect to this network. Here is the bubble family relative to our cubic containment field. The orange triacantahedron is the outside layer of this family. and it tunes the sizes of the rest of the systems. The long axis of the bubble diamond is the same length as the edge of the yellow icosa. The short axis of the bubble diamond is the same as the edge of the red dodeca. The icosi dodeca is the innermost layer. You can see the practical advantages of these 14 directions in common when you want to compare the systems of the sphere and bubble families. Laying the foundation of defining clear-cut structural and numerical constants tunes all of the variables into one synergetic whole. Here is the sphere family inside our cubic containment field. The octahedron is at the center with its 6 outside corners sharing the green locations in common at the center of the squares. The rhombic dodecahedron, our dodeca, is formed around the octa using 8 modular units that are 1/4 tetras. The coupler is constructed around the R-dodeca using 4 half-couplers that are 1/2 the size of the larger coupler. The tetrahedron connects 4 corners of the cube. The coupler and the tetra shown here are the same volume and can be paired together to define the directions of the cube. We will explore these interconnections in subsequent videos. What gets interesting is when you begin to build physical models of the synergy between the sphere and bubble families. It starts simple by dividing the sphere family structures by GR and GR squared. There is an icosa inside any octa by using this division. Following the red directions, the R-dodeca can fit exactly inside any larger icosa. The 4th portal of the naturalmodular.com website, there is a guide to building many examples of the synergy between sphere and bubble families. Embedded in these structural memories are the solutions for your local building problems.